All right, so we're continuing. We looked at Laplace, block diagrams, and we sort of started getting into the mathematical modeling, but this is looking specifically in more detail at the mathematical modeling, and we're going to end up looking at the DC motor as a sort of example or case study. So let's have a look through this. First of all, this is how mathematical modeling fits into the overall control system design process. So you start your process. I've just tried to represent it as a flow diagram, and you do your block diagram construction, and to do that you also use Laplace to get your transfer functions, right? And that gives you, a transfer function based block diagram in S. And this all here, this is what we're looking at the moment, the system modeling aspect, right? So this is all system modeling. Well, if you've verified that your model is good, and that's an important step, just making sure you've got a valid model. If you have, you can proceed to your controller design and actually use your model, right? And once you've designed a controller and come up with the algorithm or the control algorithm or the kind of control logic you want to use, you can then try it and see how it works. You can run some experimental tests. Of course, you can use the model to do that, so you'd have to do the tests using a physical prototype. You could use a model prototype, and if you've done the tests and you compare the test results you're getting from your controller with the targets or your performance requirements of the system, if they match up well enough, then you can say, okay, job done. If not, then you have to keep looping around, revisiting your controller design, iterative process, right? Iterative process. So you keep going until you've basically reached your objective. So that's the general control design process, but it's based on model-based design. In fact, in industry, it's very common to use model-based design. So you have your plant modeled and your controller modeled, and when you've got a reasonable design for your controller, you might actually use what's called hardware in the loop. And then what you do is if we have our block diagram here, you got your controller, but this controller could actually be hardware. And then you've got your plant model as software, and your feedback loop as software. So in this little sketch, this part is actually a physical controller, like a circuit board with an electronic chip on it, and you plug that in to your model. And there's ways in which you can convert signals. You take your signal from your computer and you feed it into your hardware. That's your control input, and then your control action comes back into your plant model in the software, and then the behavior of the plant or the behavior of the system is modeled based on that control action. You get your feedback loop, and then you get your control action, the updated control action fed into your hardware. So it allows you to actually build the hardware, the control hardware, before you have a physical plant model. So let's look at the derivation of transfer functions and time response. Well, we kind of covered this already. This is just a quick recap. For a simple system, you start with a fundamental law, which is usually a system of differential equations. And that system of differential equations would use your basic physics type relationships like Newton, like Ohm's law, like Kirchhoff's laws, as heat transfer, etc., etc. All those kind of basic relationships. And if your system is non-linear, you can actually linearize it. There are ways of doing that. So you make assumptions about your model, simplifies it, but it allows it to be treated as a linear model then. So now we have ODEs, ordinary differential equations. Now, when you've got your ODEs, you can take Laplace transforms, and then of course you can deduce your block diagram, and then you can reduce your block diagram, as much as possible to give you your overall transfer function for your plant or for your plant plus controller or whatever, however you want to do it. Right. So that's our system. So we're going to come back to a familiar problem. This is very similar, but subtly different to a problem we did last time. This is an RC circuit, but the configuration is different now. Your capacitors, we're looking for the output across the capacitor as opposed to looking for the output across the resistor. So we want to overall derive the overall transfer function for this. So the overall transfer function would be your output voltage over your input voltage. And then we're going to apply a step input on this end to our EI. We're going to give it a nice step input, not like that. Let's try a better step. There we go. And we want to say, well, what's our output going to look like? This is our input. Is it going to look like this? Is it going to look like this? Is it going to look like this? So what's our output going to look like? And then not only we're going to look at a step input, we're going to introduce a new type of input, which is a ramp input, right? So that's something like this. So now we've got a different input. What's the output going to look like to this type of input? What's it going to do here? Is it going to converge to the input or not? So, okay, solving this one. The first thing we're going to do is we're going to use Kirchhoff's voltage law and Ohm's law. Ohm's law, of course, applies to the resistor, and Kirchhoff's voltage law applies to the full circuit. So using these two laws, I want you to write out the equations for this particular circuit, right? So using that, you can create one equation for your expressing your voltages in the circuit using the input voltage, and you can get another expression for the output voltage. So we're looking for a system of two sets of differential equations. EIT equals what, using Kirchhoff's voltage law, and EOT equals what, right? This is actually using a version of Ohm's law, right? So to save time, let me just go through it and sort of use it as a worked example. So using the Kirchhoff's voltage law, this tells us that the sum of all the voltages in a circuit equals 0. So we're going to say that EI of t is going to be equal to the voltage drop across our resistor, which is going to be I as a function of t times R, plus the voltage drop across the capacitor, which is given by 1 upon C times the integral of IT dt. On the output side, the output voltage is just looking at the voltage across this capacitor here. So on the output side, we just have 1 upon C integral I t dt. Right, so having done that, we've got the equations which are basically differential. You might not see a differential, but you're seeing an integral, right? And you know integrals and differentials are related, so in this case we don't actually have a differential term, but we do have two integral terms, so it makes it a system of ordinary differential equations just the same. So what we're going to do next is take Laplace of these two equations we have. So we're going to take Laplace transforms of our equations. I probably have to write them out again. In fact, I need just one second. Let me give myself an extra space to work here. So we have EI equals IR plus 1 upon C integral IT dt. And on the other side, on the output side, we have E out of T with 1 upon C integral IT dt. So taking Laplace, that gives us EI of S. Laplace of I TR will just give us IS of R. That's a simple transform there. Plus, now we have an integral. And when you have an integral, you have to divide by S. So you end up with 1 upon CS IS. Right? That's the Laplace transform of this. Right? On the output side, we have another 1 upon C, and the integral, we resolve that by calling that 1 upon S. If you have a differential term, like dx by dt, and you take the Laplace transforms of that, that's going to give you SXS. Right? If you have the Laplace transform of an integral term, that gives you 1 upon S times X of S. So that's what we've applied here. Right, so what we could do now is sort of slightly rearrange each of these terms, because we've got two i's here. So let's bring the I outside, and then we have R plus 1 upon CS. We can cross multiply there. So that gives us RCS over 1 plus RCS plus 1 over CS in the denominator. Right, and nothing changes on this side, on the output side. But now we have an expression for our input and our output, so we can divide one by the other to get our overall transfer function. So our output over our input is going to give us IS over C CS over IS times right, so we actually cancel this, and we also have to cancel this. So that gives us 1 over 1 plus RCS. Okay, that's similar to what we got last time, I think. And I made the point last time that this is a first order transfer functions like a typical one. And for a first order transfer function, the characteristic of a FO, first order TF transfer function, is tau, time constant. The characteristic of a first order transfer function is tau, and tau is this term RC. So the transfer function, C over R is going to be equal to 1 over 1 plus tau S. So that implies, in this case, tau equals RC. That's a reasonably important result as well. So we can express it in its standard form like this, like I just wrote it on the previous slide. And our time constant tau equals RC. So you realize the physical elements in the system, the resistor and the capacitor, their values. That's what defines how fast this system responds to inputs. We can actually express it or represent it like this. So we've created a model now of our RC system. This is our RC system model. Our little electrical circuit with a resistor and a capacitor. It behaves like this. And now we can use our model and get an output time in response to a step input. Okay, well, let me write it out. So this is very similar to what we did before, actually. So let me just follow my PowerPoint notes. So we're multiplying out by the input to get the output. So our output is our input times our transfer function, and our input unit step 1 upon S. All right, so that's gone in here. Right, so we've got our 1 upon S here times 1 plus tau S plus 1, 1 upon tau S plus 1. So we know that we're going to take partial fractions now, A upon S plus B upon tau S plus 1. And when we find the values for A and B, we find A is 1 and B is going to give us minus tau. Right, and you could prove that very easily by just equating the terms as usual. We could divide top and bottom of this fella by tau, right? So that's how we get this final expression here. The output in the S is going to be 1 upon S minus 1 over S plus 1 upon tau. Right, now we do the inverse Laplace. We know if our inverse Laplace is just going to give us 1. And we also know inverse Laplace of this, because this is in the form of 1 over S plus A, where A equals 1 upon tau. And we know the inverse Laplace of that is going to be e to the minus at, right? So that's going to give us e to the minus t upon tau. Right, so that's our inverse Laplace. Right, so that's our output. Now, if we have a special condition where if t equals tau, what's going to happen? If t equals tau, this is going to go to 1. Right? So we can actually evaluate that even if we don't know what the value of tau is. we do know that at this special condition where t equals tau, then our output C of t is going to be 1 minus e to the minus 1, which is, of course, pretty calculable. Right? E to the minus 1 is 0.368, right? So if we subtract that from 1, then we get 0.632. So that is going to be the value of the output at the time when time is equal to the time constant. And that's going to be the same regardless of the system. If the system has this property, this characteristic of being a first order type system, you're always going to get this. And what's more, you could calculate the same thing at other values. So you could look at it 2 tau, 3 tau, any multiplier of tau, of course. You could calculate, well, what's my output going to be at that value, because the taus cancel and you get a number for your exponential term here. And of course, as time increases, this term is going to get smaller and smaller. Right? And we can see that here, the difference between 1 and 0.63 is greater than the difference between 1 and 0.86 and so on, right, at 2 tau. So this slope, in other words, the characteristic of this slope is more or less, it is identical for every first order system. Once you can calculate what the time constant is tau for any first order system, then you can get that shape of curve. But the actual exact profile of it is going to be affected by what the value of tau is, and tau is determined by RC. So as you change your resistance and your capacitance, then you're going to be changing tau. Time response to a ramp input. If we now have our same first order transfer function, but now our input, instead of being 1 upon s as a unit step, we do 1 upon s squared. This is a unit ramp. Now, refer to your Laplace tables, because we'd have mentioned it and looked at it very quickly then, because we have different types of inputs. This is the expression 1 upon s squared is the expression for a unit ramp. All right, so that means that the equation, the basic equation, is y equals x. Right, or in time terms, y equals t. Right, so your output is always going to be equal to your time. At time 1, y equals 1. Time 2, y equals 2, etc. Right, so that's your unit ramp input. And now, because you've got the s squared term, of course, it makes it more complex, and you're going to have to do a repeated root when you take your Laplace, your partial fraction. So here's the repeated root, right? So when you do that, the second root is subtracted. So a over s squared minus b upon s plus c upon tau s plus 1. And when we derive our values for a, b, and c, a is 1, b is tau, c is also tau, right? But now for c again, we divide top and bottom by tau. And so we end up with this equation for our output. And again, we can ask what happens as time goes to infinity. Well, now time goes to infinity, this term is going to go to 0, but you're still going to have a t. Your time is still going to be increasing, and you have a constant factor which you're subtracting from it. So you're always subtracting the time for a first order system. You're always subtracting the time constant from your actual time as time goes to infinity. So you have a 1 time constant lag between your output and your input time. Okay. because remember it's a unit ramp, so time is basically the input. So this is what it looks like when you sketch it. This is the black line is the ramp. Output equals the ramp, RT equals T. But your output, the red line, this term here is responsible for this part of the line before it settles down to a sort of steady state error with a 1 time constant lag and a 1 time constant delta between the input and the output. Right? So that lag works in both directions. It's a 1 time constant time lag, and it's a 1 time constant error in the value at any given time. So at 4 tau, you have a 1 time constant error. But this part, this is the transient part, and that transient part is dominated by this decaying exponential term. Once that exponential term is decayed, then you get into a condition with the steady state error. And this is a standard first order response to a ramp input. So we looked at the response to a step input. This is the response to a ramp input, and we can see the steady state error and the time lag, both tau. Let's jump into looking at the DC motor. As I said, DC motors used for servo systems, usually speed control. When talking about a servo, it tends to be speed control as opposed to a stepper motor, which is used for position control usually, or to move a device to a specified position. And they are popular actuators. So here are some examples of where you'd find servo motors or DC motors in actual devices. And like I said, they're pretty much ubiquitous. Conveyor belts, robot arms, crane lifts, aerolon. Well, aerolon, some might have electric motors controlling them. A lot of aerolon and other systems on an aircraft tend to be hydraulic, but there will be some interface between a hydraulic system and an electrical control system in aircraft as well. So really, you name it, it's probably got some kind of motor control in it if it's a moving system. Drones, another one. In fact, drones are quite an interesting control problem because they have incredible abilities to sort of maintain stability, not only sort of height, but also pitch and yaw. Be able to resist breezes and maintain a constant sort of GPS position. So drones really have quite an interesting set of controls in them to vary the power of those. If you have a quad drone like that one, the 4 motors for each propeller, and be able to vary its positions, orientation, speed, trajectory, etc., etc. So drones, really, really interesting control systems there. And now, of course, one of the interesting things that's happening is that there's a huge proliferation of basically drones for people, this sort of vertical takeoff landing type small electric aircraft, which are designed for sort of 1 to 8 people or something like that. And they're building off the drone technology, using some of those same drone technologies. Some of them have just the quadcopter type layouts, others have tilt wings. So they have maybe some kind of lift function when the wing is oriented in one direction, and then the wing will tilt forwards so you can get flight in the horizontal direction. That's also quite efficient. And the fastest sort of drone like that, VTOL or eVTOL, electric vertical takeoff landing vehicle, I think it just hit a sort of speed record of about 200 and plus miles per hour. So pretty fast, and of course you could use it in a confined space. You could land it in your backyard or whatever, potentially. So that's an exploding area of innovation, and a lot of new products coming to market pretty soon in that domain. So and then this is one of my favorites, D-Bot. I think I showed you a little video of D-Bot in instrumentation, right? So he's my friend, keeps my house nice and clean. But again, loads of controls and lots of motor control stuff. Trajectory, once it's mapped, is set point course or its desired trajectory, then of course the wheels have to take it in the right direction. It just uses 2 wheels and a free rotator pinion at the front. So with those 2 wheels, it's able to move at its preferred speed and in the right direction. So all of that uses motors. So let's just revise or learn for the first time maybe DC motor theory. Fundamentally, basically all you're doing is passing a current through a wire in a magnetic field. And because you're doing that, by Lenz's law, then when a current is flowing in a conductor in a magnetic field, then the conductor experiences a force acting on it. The direction of the force is defined by the left-hand law, which I'll talk about in just a second. If you have a configuration like this, where you have the current flowing in a loop, a wire loop like this, then of course you basically have a force acting at both sides of this wire loop, because both sides are passing through this or transecting this magnetic field, and as a result of that you get a rotational force or a torque acting on this little configuration. That torque is going to cause a rotation, and that's the fundamental concept of your electric motor, your DC motor, right? So that's the basic principle that's used. Of course, one wire won't make a very powerful motor, and it has a few little problems in it. So you see we have this thing called a commutator, and for a DC motor, power is supplied through a commutator. Let's talk about why a commutator is needed, but first, based on Fleming's left-hand law, this tells us which direction we're going to get thrust based on the direction of the field and the direction of the current in a conductor. So everybody hold up your left hands, point out your index finger and your second finger, hold your thumb up. That's the left-hand law. The pointy finger is your pointer. That's the one that shows the direction of the field. Your which one's this? The second finger, let's call it, is the direction of the current, and the thumb shows you the direction of the thrust. So if we apply our left-hand law to this particular little configuration, so you have a rotor which is free to rotate, right? And on that rotor, around that rotor, is attached and wrapped around a conductor. And we're looking at a cross section here, right? And what we're looking at is current flowing away from us on this side, and current flowing towards us on this side, on the right side, right? We have a wire wrapped around this 3D rotating rotor. What's going to happen is this, as it passes through the wire on the left-hand side, the field direction is north to south, so point your pointy finger to the right. The current is going away from you into the page or into the screen, so point your second finger into the screen. That's the direction of the current. The X is like the end of an arrow, so it's showing that the current is moving away from you, and therefore your thumb shows you which way the force is acting on the conductor, which will generate torque in the rotor. So the force is acting down. Now for this one on the right hand side, the current is coming towards you, so the field is in the same direction, so you rotate your hand kind of 180 and point your second finger, the current finger, towards you instead of towards the screen, and now you can see the force acting on this conductor is going to be pointing upwards because your thumb is going upwards. Right, so that means you'll get a rotation counterclockwise. If we call that positive rotation, we got a positive rotation in our in our rotor. Now the problem comes when this rotator, like this particular side of the conductor, rotates round to about here, let's say, which is what we're looking at in the second picture. So now let's look again at what's happening. The top conductor now, which was previously on the right hand side, and has the current coming towards us as we look at this cross section. Let's use the left hand rule again, Fleming's left hand rule. So the field direction is sort of down, well, there's left to right. The current is facing towards us, and so as you can see, if you rotate your hand to the right angle, the thrust will be the way the blue arrow is pointing here, right? And the thrust on this side is the opposite way. So basically, rotation, positive rotation is this way. The rotator spun around, the rotor is spun, but now when the conductor, encounters effectively an opposite field, because it's on the other side of the permanent magnet, the thrust reverses. So if we were to leave the situation like this, where the current flows in a consistent direction through the hoop, through our little wire loop, if we leave the current flowing in the same direction throughout its rotation, then what you're going to get is, when it gets to this point, it'll have some momentum, it will carry it a little way, probably to about here, but then the thrust acting in the opposite direction will stop the rotation, and it will cause it to rotate back. And you'll just get this seesaw effect of the motor rotating back and forth, back and forth, back and forth, right? And that's not obviously what we want. So what we have to do is somehow, when the motor, or let's say when this wire gets past a midpoint of rotation, you actually switch the current. So then this wire, instead of having current coming towards us, will have current going away from us. This one, instead of having current going away from us, will have current coming towards us. Right? And then instead of having the blue arrows, the pen isn't doing very well with little dots. Right? Every time I do a dot, it wants to come up with a menu. Right, so instead of the situation here where you're rotating back and forth and seesawing, now if you flip the current in this in this conductor here, well, flip the current in the hoop, right? So you reverse the direction of the current. Then the current will be going away from us here, and the force will be going this way instead of upwards. And that's what we have in the bottom left now. So now we've rotated round and we're maintaining a positive torque, which means that instead of stopping and reversing, the rotor will now continue to accelerate in the same direction. So that's what we have to do. Every time we go past, a midpoint, when one of these conductors goes beyond a vertical, you have to switch the current. So basically you switch the current every, well, in this case it's going to be 180 degrees, not 90 degrees. Right? So every time you have a half a turn, you switch the current. And that keeps the motor rotating in a constant direction. And you do that using something called a commutator. Right? And actually, on the previous slide, you can see a commutator here. So the DC current applies to these pickups, right? And the pickups are rubbing on this device here. This is in fact your commutator. So it's a contact really. So you've got contacts rubbing on a pickup, and as this rotates, if you imagine this rotates in a counterclockwise direction, as it's rotating, when it gets to this point, it's a little tricky to draw on this. As it gets to this sort of point where the split is like that, then of course at that point, as you continue past these contactors, the current's going to rotate, going to reverse, because it's always flowing in a specific direction through the contacts, but now it's reversed the direction in the wire. Right, so that's how a commutator works. So that's just a two segment commutator, and it's shown here, not very clearly on this diagram, but This is the breakpoint. Right. So as our rotor moves in an anti-clockwise direction, right now we have a current on the this wire, or this side of the wire, going into the screen, coming out of the screen here. As we rotate around, as this rotates around, and then your pickups come to this point, that current is then going to reverse, and you'll get a positive torque in the opposite direction. So if we map the torque against position, you basically get maximum torque when the conductors are horizontal. That declines down to zero torque when they are vertical. So, but then as the current reverses and they continue their motion through momentum into the next part of the magnetic field, then you start to build up torque again to a maximum point here. So unidirectional motion, but the torque is very lumpy. Just through the whole rotation, you have two peaks of torque. In between, your torque drops off, which means that the acceleration of the rotor is going to be very inconsistent as well, and not ideal. So what do you do about that? Well, instead of having a 2-segment commutator, you have many more segments. This is a 16-segment one here. So I'm just showing where the boundaries for each commutator are. So you're switching the current, well, applying current and then switching the direction of that current to each of these wires in turn. Right now, let's say this is connected to this wire. Well, no, it'd be connected to this wire. And this one here connected to this wire. All right, so right now, this one's going to have current going into the screen. This one's going to have current coming out of the screen. Then in a second, like as the motor rotates, and what you're doing is you're connecting wires or applying current through wires that are in their maximum torque zone, right? But in a short while, you're going to kind of rotate around, and then you want to apply torque and current and torque instead, to say like you want to apply it to this one and this one, as these ones. No, let's do that. Let's go up here. This one and this one, they'll get activated when they come around to the connectors, and then they'll be in their sort of maximum torque zone, which is sort of here. So when the current is flowing through that green conductor loop, then you're going to get like a maximum current or maximum torque generated from that green pair. And that's how you end up with a basically flat torque curve right through the rotation of the motor through 360 degrees. Because really you might have little dips here, but it doesn't show up too much. You get a nice consistent torque by having a high number of windings. Each commutator segment is connected to a winding, so you have more windings, gives you a smoother torque in the DC motor. In reality, of course, it's not just a single wire that is connected to one commutator segment. It's a bunch of wires, and by doing that, of course, you're able to pass more current and therefore get more torque out of the motor. So this is showing permanent magnet DC motor. Okay, so that's the kind of concept of how a DC motor works. We're going to dig in now to the modeling aspect of it. And we're looking here at a schematic of the DC motor. And let's just walk through it then. On the left-hand side here, you have an applied voltage, which is your DC voltage applied to the motor from a battery or from a rectifier. If you're running it off some AC source, you have to rectify it and eliminate the AC to give you a DC current. That gives you your input voltage. You may amplify that, so that'll give you, using a transformer of some sort, increase the voltage internally within the motor winding. So what we have here, this part here reflects the motor windings, and this here, this is the motor shaft. Okay, we have a sort of lumped resistance, which is of course the resistance of the entire winding. We're lumping it into one, representing as one single resistor, and this likewise is our lumped inductance. Right, so we got a RL circuit effectively in this case, L being L for inductance. Remember, inductance, whereas capacitance lags on the circuit, inductance leads on the circuit, and it's the voltage across an inductor is given by the current through the inductor times, big button, given by the inductance times the first derivative of the current through the inductor. So you're going to have inductance and resistance in your motor windings. One of the downsides of a DC motor is you basically have internal electrical drag in the form of back EMF, and your overall current, if you like, that flows through this circuit, call it IA, is the difference, it's the function of the difference between your driving EMF or your amplified EMF and your back EMF. So those sort of work against each other. So the back EMF is like an internal resistance voltage, and the difference between the voltages is what's going to generate a current, and therefore the torque and the drive. Now, we have some other elements on the schematic as well. We've got a transmission with a ratio of n. That means for one rotation of your driving gear, you have 1 upon n rotations of your driven gear. You have to take that into account, and then what you're seeing here is a kind of lump, literally it's an inertial load. So we have JL here, the load inertia. We notice we also have another JM here. This is the inertia of the motor. So the motor itself also has an inertia because it's got windings, those have a mass. It's rotating that mass. So if you have a rotating mass, that is an inertia. So the motor has an inertia, and also the inertia has an inertia. We also have B on each part. So BM, that's the motor friction. So B is friction. And we have a BL, that's load friction. So in its free condition, there's not really any friction on the inertia, but if you were to put your finger on it, it's like, this is the schematic for a clutch plate. So if you apply a finger or something rubbing on this inertia, so in the actual lab, you might touch it, and it could cause friction and slow down or cause an additional drag on this inertia, which could affect the overall speed of the system. Let's get into the governing equations for this system. The first equation we need is Kirchhoff's voltage law. Remember, Kirchhoff's voltage law says that sum of all the voltages in a circuit, let's use K, equals 0. So applying this to our circuit here, right? So the sum of our EMF, our driving EMF, minus our voltage loss due to resistance, minus our voltage loss due to the inductance, minus the voltage loss due to the back EMF, is going to equal to 0. So that's the first equation we have. The voltage loss, so VR equals IR, right? So it's going to be IA times RA. VL, the voltage across our inductor, is going to be our inductance times dIA by dt. So basically, inductance works in such a way that it's the rate of change. It creates a voltage that's proportional to the rate of change of current times the proportionality constant, which is our level of inductance in the inductor, right? And then EB is a voltage, so that is as is. But it's a voltage which actually is a function of speed. So we could have some constant k, so set k subscript b, times our speed, which is, let's call it omega m, motor rotational speed. So when we write that out, we just say this Kirchhoff's law of EA on one side and the other terms of the voltage losses in the circuit on the other side. And as I said, our back EMF we can represent it as some constant, our EMF back EMF constant KB times d theta by dt, which of course is the same as KB omega m, let's call it. Omega is rotational speed, theta is rotational position. So the first derivative of rotational position is rotational speed. We already said back EMF is created due to that voltage in the armature winding as it moves through the magnetic flux. We have our first statement basically there. Let's look at another defining governing equation. We also have Newton's laws of motion at work. Why? Because of this part. Right? We're accelerating a mass, if you like, or an inertia, depending on how you look at it. We have to accelerate the inertia, accelerate the mass. But in reality, we have the lump on the outside, this part, and we also, the motor itself also has mechanical dynamics in it. It has a mass of its own or an inertia of its own. So we have to accelerate the combined, the combined inertia of both of these. Now, we have to take into account the gear ratio between the two as well. But if we do that, you can see that this isn't changing, this is constant, so they're rigidly connected. Okay. So we could actually get an effective inertia for the whole system, and apply it at the motor shaft. Right? And we can get, likewise, we can get an effective friction for the whole system, this viscous load or friction load for both the inertia itself and the motor, internal friction in the motor, and we can apply that at the motor shaft as well. So we're going to apply everything at the motor shaft, going to bring the inertia back through this transmission ratio so that we can say it acts at the motor shaft. So we have to calculate the total inertia and the total viscous friction, and the equivalent inertia at the motor shaft is the inertia of the motor, Jm, plus 1 upon n squared JL, the inertia of the load. Why 1 upon n squared? Well, hopefully you know that from mechanics of machines, but that's how you bring inertia. That's the impact effectively of the inertia due to the gear ratio. So what this says practically is if you have a higher gear ratio, basically the effect of the inertia, or the way the inertia feels at the motor shaft, is reduced, right? So if you have, say, if n equals 3, 3-to-1 ratio on that transmission, then JEQ might be equivalent to Jm plus JL upon 9, right? So you're really reducing the effect of the load inertia by applying that transmission ratio, the n, right? But it's a function of n squared. And likewise for the friction, the load friction divided by the ratio squared to give you the load part of the friction, and this part is the motor part. Right, so you add them together to get the overall effect. To get position relationship, again, if you have, say, the motor is at a certain position in degrees, then one rotation, or let's say a quarter rotation, a 90-degree rotation of the motor shaft, which will be at 90-degree rotation of the motor shaft here, will result in not a 90-degree rotation, but 90 divided by n degree rotation at the load shaft, right? So again, the gear ratio has to be taken into account, so you can relate the position of the load to the position of the motor. So now we can get to actually calculating or getting an expression for, based on Newton's laws. And we're just applying Newton's laws, F equals ma, but of course in the rotational dimension. So force is torque, m is mass is inertia, and x, or displacement, instead of being linear displacement, now is rotational displacement. So this is our m times our a. This is our inertia times rotational acceleration, is going to be equal to our torque. That's our F equals ma, but you also have to subtract the torque, that is the drag torque caused by our equivalent viscous friction. That's viscous friction constant, BEQ, multiplied by the speed of rotation to give you your drag torque. And then our motor torque, which is the driving torque of the system. The torque generated by the motor is going to be given by a motor torque constant, Ka, times the current. So really, as the current goes up in the circuit, in that motor circuit, then the torque goes up proportionally to a motor torque constant. And this really, this torque constant will depend on things like the size of the motor, the number of windings, the resistance in the circuit. So all the things that affect the characteristic of the motor can affect the amount of torque that's generated by that motor for a given current. So it's all the electrical elements that make a difference to the motor torque constant. So of course you'd ideally want that to be as high as possible, because if it's a high motor torque constant, you get a lot of torque for a specified current. So now we've got those, kind of on this last slide, we've got these last two slides, let me say. Between this slide, which shows the electrical governing differential equations, and the next slide shows the mechanical governing differential equations, well, and sort of an electrical one thrown in here. But, so we've got a set of electrical equations and a set of mechanical equations. Now we go through the process of taking Laplace transforms so that we can combine them. And that's, again, just to remind you, one of the big benefits of taking Laplace. So let's take Laplace, first of all, of our electrical system. And let me just note, write in here what the time-based differential equations were that we're using here. We said E A equals our voltage across our resistance, which is RA IA, plus the voltage across our inductance, which is LA DIA by dt, plus our back EMF EB. So we're taking Laplace of each of these. So Laplace of this just gives us capital EA as a function of S. When you take Laplace, you normally capitalize. That's the nomenclature we use. Minus, we're taking our EB, taking Laplace of it, and put it on the left-hand side. So this is our kind of net voltage, taking our resistance. That's straightforward enough. All you're doing is taking the Laplace transforms of your IA, because that's the time-based function. RA is just a constant. When you take Laplace, it just gives you IA of S. This is the first derivative. So assuming zero initial conditions, then this is going to, when we take Laplace of this, it's going to give us S times IA of S. Right? And so that's what we have here. And our LA is a constant, so that just remains. Rearrange this to get an expression for IA. We've got other sets of equations that we need to take Laplace of as well. We have this one. So if we take Laplace of this, TS equals KA IAS. If we're taking Laplace transforms of this, then we have JEQ times, now we have an S squared here because you have the second derivative of theta. Right, equals T of S minus BEQ, that's a constant, times S theta S. Right? So remember we have an equation here for BEQ as well. This one, so we have to substitute that in. So that's how we take the Laplace transforms of the mechanical part of the equation. This is a rearrangement, that's all. We just rearranged it into a slightly different form. This is our speed, this is our position. Now we know omega equals, if we say omega is a function of t, equals d theta by dt. Right, so if we take Laplace of this, then we get Ws equals S theta S. So that's all we have here. Right, so don't get worried about that part. It's just the fact that it's just a relationship between speed W and position theta. Finally, our output load position. We have theta as our motor shaft position. No, sorry, C is our motor shaft position, theta is our output position. You see what we have here, we kind of have a cascade of relationships where our I goes into here, our T goes into here, right? And then we've got a theta that goes into here. So that allows us to draw this now as a series of blocks, right? And effectively the output from each of these transfer functions feeds as an input to the next one, right? So remember, anytime you have a transfer function, you can put that into a block with an input and an output kind of thing, right? So that's what we're going to do now to create the block diagram. And this is what it looks like. The block diagram completely follows the equations we had on the last slide. We have a difference between our input voltage and our back EMF. We know our back EMF is generated by something, but let's just take that as being a difference for now. And that then becomes an input, and if you divide that by SLA plus RA, then we get our current, right? So we have here that input EAS minus EBS. It's the difference so what we're saying here is, okay, well, this looks like a feedback loop now because we know our EB is a function of something further, the speed of the motor. So that's like a negative feedback loop. We're applying a known input voltage, and the difference between this is what's going to accelerate our system. And we identified from that set of from the electrical system equations that if we divide the difference between our applied EMF and our back EMF by RA plus LAS, then that's going to give us our voltage, our current in the circuit. That came from here. Our current in the circuit is the difference between the applied voltage, or that I called it the net EMF in the circuit, divided by SLA plus RA, right? So that's exactly what we're representing on the block diagram in this first block. Then we also found out from the Laplace transforms that our torque, the overall torque generated by the motor, is the current times the motor torque constant, Ka. So, when you, so basically we're just taking the current, multiplying it by Ka, that gives us our torque. And then the torque applies to the mechanical aspect of the system. And, F equals ma, so the F, in this case, is a rotational system, so that's our torque times our inertia. F equals ma, so torque divided by the equivalent inertia and the friction is going to give us the speed of the output. And then we need speed to give us our back EMF, so that's where our feedback loop comes. Multiply it by our back EMF constant Kb. It goes back to the beginning of this block diagram. We really want to be able to determine the output position of the inertia, so we have to divide by S to give us to go from motor speed to motor position, and then we have to divide by N, our gear, to give us our output position of the inertia. So let me just take you back to the original schematic to this page. Right, so I think we said this is the speed and this is the position of the motor, and this is the position of the inertia. Right, so now we've gone right through the system and we have a block diagram that defines an output motor position. So now we've actually gone through the process of creating a mathematical model of the circuit, and from this we can get quite a number of transfer functions. We could get this transfer function here. We could resolve this loop and get a transfer function for W, or our motor speed, as a function of our input EMF. Right, that's this one. We could also get extend that and take into account these are the two elements on the end. So we can get our position of the load as a function of our input EMF. Right, so both of those we can accomplish. But we could also simplify this. You can simplify by getting rid of some parts which are going to have less contribution to the overall behavior of the system, the fast electrical dynamics. And that's primarily this inductance. It's going to be a relatively small contributor to the overall behavior of the system. You can sort of neglect it and simplify the whole thing. Another thing you could eliminate is you could say, well, the friction is pretty minimal compared to the effect of the mass in terms of how the system behaves, how it accelerates, and so on. So there are certain elements you could take out of this to simplify the model, and that's again what we're going to do. This is the transfer function. I said the first transfer function is between motor speed and our input voltage. This is the transfer function. All it is just taking our closed loop, using our closed loop transfer function formula. G of S equals, let's say GCL equals forward path over 1 plus open loop. Remember that from our block diagram lecture. And we've applied that to this little loop here. Right? So we're going to reduce that down to a single block. And this is the transfer function for a single block between our input EMF and our motor speed, and the relationship between our input voltage and our load position, well, we just extend this a little bit to include NS. Right, so we just multiplied this block which we've created, which says EA. We've got a block that says GWE S, and that sort of swallowed up our closed loop feedback, which is our back EMF. Then we feed that into two more blocks in the block diagram on the previous slide. One has 1 upon S and one has 1 upon N to give us our output C of S. That's these two blocks here. Right? So when we do that, all we have to do, because these are blocks in parallel, you just multiply them together. So C of S over EA of S is going to be equal to GWE of S times 1 upon S times 1 upon N. Right? And so all of this is the same, comes directly from here, but we just have this N and S term on the denominator there. So what we can do now is simplify. As I said, we can neglect the inductance in the armature, which is the motor windings. That's the first thing we can do. So if we do that, then this equation here, if we neglect that inductance, we're eliminating this term, right? And if we do that, then all we're left with is this term, and this term. That's what we have here. So now you notice the highest power of S on the numerator, on the denominator, sorry, is S. Before you had an S squared here. So basically what we've done is we've reduced this transfer function from being a second order to a first order transfer function, because the highest power of the denominator, S in the denominator, is the order of the system. Right? And then finally, we can rearrange this. We see this typical transfer function form, because this is equivalent to, let's say, A over S plus B. So it's a transfer function in this form. This is a constant, 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 a constant, right? So every term in this equation now, except for S, is a constant. So we can say this is our typical first order transfer function. From there, you can tell me what's the time constant. So we're going to look at a mass spring damper system now, which I think will be familiar. We have a mass here, we have a spring with a spring constant K, and we have this F, which is a damper. So it's called a dashpot damper. Basically, if you know what a shock absorber on a car looks like, that's a form of a damper. So it's something like that, where you have what's effectively a hydraulic ram. Basically what you have in a car suspension system is you have this shock absorber. One end is connected to the vehicle body, probably underneath the wheel arch or something. And then the other end is connected through this shock absorber to the wheel, right? So you also have a spring around this as well. So this is actually a mass spring system. But just looking at the damper's filled with fluid, so that as the wheel moves up and down, then the fluid actually, there's a tiny little hole at the top of the shock absorber that allows the fluid to be compressed into a chamber. So as the wheel, hits a hole or hits a lump in the road, or a speed hump or something, then the wheel's forced upwards, but the rate of motion of the wheel is slowed down by the damper. And that's the same as what's represented here. Right? That's what it's shown with the kind of this ram and a kind of cup shape So this is really showing a piston, a hydraulic piston, which is what the damper is. With the system, what we assume is that we're applying our input at this end, sort of moving firstly the spring, which is connected in series in this case to the mass, which is connected in series to the damper or the dash spot. And these sort of mass spring damper systems could be configured in different ways. You could configure them in parallel. You could have maybe a spring connected to the mass with a damper in parallel. You know, there are different configurations that could be used, but in this case we're just looking at it as a series of elements in this particular system. And the input, as I said, is applied here. So if this end is displaced by some value xi, then what we're interested in, bearing in mind that the damper is attached to a rigid element, so this part, this can't move, this is rigidly attached to the end wall. We're interested in what's the motion of x out, right? So if you could either apply a step input, where you're moving it instantaneously from point 0 to point 1 or something like that, you know, just a known displacement, or you could be applying an oscillation. So you could effectively be oscillating this back and forth, and you're looking at the relative oscillation of your output. It could be either way that you're using this particular mass spring damper system, but for now we just want to model what's the relationship between our output and our input, and therefore what we ultimately want to get is our output as some function of our input. The first thing we have to do when we're modeling, like we did with the other systems, that was the RC circuit and the DC motor, is we have to identify the equations of motion using Newton's law. Right, so what laws do we have here that we could use? So by balance of forces, we can say that the acceleration of our mass is equal to the forces acting upon it. So you have a spring force that is called that Fs, acting to accelerate the mass in a positive direction, and you've got a resistive force which is coming from the damper that would generally, you know, if we're looking to, if we are accelerating the mass in the positive direction, the damping force is going to be a retarding force on the mass's motion. Right, so that's what we've got represented here. This is the spring force. This is the retarding damper force, and the damper force is equal to the damping constant F times not displacement in this case. The spring force is a function of displacement, but the damping force is a function of the velocity, the first order derivative of the displacement. So it's the velocity of the mass that will determine the damping force. If the mass is accelerating or has positive velocity to it, then you're going to get this retarding damping force minus F dot x, or minus F times the speed of motion of the mass. And then of course that is balanced by Newton's law against the acceleration force, which is mx double dot, or ma, right? X double dot is acceleration, of course. So now we've got that basic laws of motion, we can take Laplace transforms. What are Laplace transforms? We're assuming zero conditions. That's important because we've got two derivatives in this equation. We've got a first order derivative, which is from the damping force, and then the second order derivative from the acceleration force. So we are going to get from our previous equation k, which is a constant, times xis minus x out s, that's the spring force in Laplace form. This is the left hand side, so we're going to have minus our damping constant, times the first derivative of x, so that's going to give us x out s times an s for the first derivative. So that's the left hand side, and then on the right hand side we've got mass, which of course is a constant, times x out s times s squared. How do you get that? Well, I'll go back to here. We're just transforming, we're taking the Laplace transform of each element here. So this is where we get our k x is minus x out s. And the Laplace transform of this one, like I said, is times s, and this one so I think that's pretty clear. This is the same expression. Now what we could do is rearrange this, because what we really want to get is our output as a result, as a function of our input, this form. So if we put all the output terms on the right hand side, keep the input terms on the left hand side, then we can kind of cross divide, right? So we're combining all the x outs and dividing left and right by x in, so you end up with this k over this part, and this part, right? So k over s squared m plus sf plus k. That is our model in Laplace for our mass spring damper connected in series. That could then, of course, be put into a block diagram, and then whatever our input is, we kind of pass it through, multiply input by our transfer function, and that will give us our output. Convenient form, block diagram form for our mass spring damper. So we could describe this now as our plant model. And we might want to apply position control. So trying to control the position of the max, which is x out, and we might have a varying demand position or desired position x in, and so the set point x in is moving. So we could use our plant model then in a larger closed loop feedback system. So we could say R is actually our input into this, and we're going to have a negative feedback system here. We're going to have a controller, let's call that GC. All right, and then we're going to have our plant model, which we've just derived as this. And of course I've run out of space. So this is our output x out. Now we're going to take a feedback loop, sorry about the bad drawing, which might have a sensor to get our negative feedback. So now in real time, this is our output x out, which is also what we call C of S, our output. This is our plant model, and this is x in here and x out on the other side. But what we want to do now is take this transfer function, and like we did with the first order systems where we express them in terms of time constant, I want to express this second order transfer function for the mass spring damper in what we would describe as our normalized form. So for that we're going to remove our physical variables. Now the physical variables for this system are what? They are our gain, our spring constant K, our damping constant, well we have it as C, we had it as F just now, it magically changed to C, but that's C above was F, M is the mass of the system. How do we remove these physical variables and normalize? Well, we want to get it into a standard second order transfer function form, and this is the standard second order transfer function form. The second order system is described as, this is called the prototype transfer function, or the standard transfer function for a second order system, omega n squared over s squared plus 2 zeta omega ns plus omega n squared. And omega n squared is the natural frequency, right, as stated here, and zeta is the damping ratio. Omega n is the natural frequency, and zeta is damping ratio, right? Natural frequency omega n, damping ratio zeta. If we rearrange this into this format, then what do we get? We're going to divide top and bottom by m to do that. And this is going to be f upon m s and k upon m. All right, so therefore we could immediately say that k upon m equals our omega n squared, and we can say that f upon m equals 2 zeta omega n. So we have identified these important relationships. We'll come back to these in just a minute. Let me show you this little graphic first. This is sort of a GIF or whatever, a mini video. So what we have here is a mass spring damper system. Now this one is mounted slightly differently because the mass is connected to the rigid wall by a spring and a damper in parallel. The green one is the damper. This one up here is the spring. So what happens when we excite the mass, or let's say displace the mass and release it, then we're going to get something like this. And so basically displace the mass and release it, and what you have is oscillation, which is decaying over time. So you have three plots here. The bottom, this is the length of the position, let's say. Velocity follows the first, same profile, but of course velocity now is the first derivative of this length, and then you have acceleration, which is the second derivative of the length. So they're kind of moving, these three would be moving out of sequence with each other, of course. So you just see the damped oscillations eventually decaying in magnitude as time proceeds down to 10 seconds. The damping almost stops the mass from vibrating. All right, so coming back to our identity, which I drew by hand above, we already got this, although we're calling ours C. I don't know why I switched nomenclature, but let me just manually change this back to F, because it was F before, I guess. So if we have F upon M equals 2 zeta omega n, and omega n is root k upon m. Right, so that's how we get our F upon 2 root km. We related our mass spring damper system back to our natural frequency and damping ratio in a prototype second order transfer function. So if we want to determine what's the natural frequency of a mass spring damper system, the natural frequency or the oscillating frequency when the system is undamped is going to be a function of the spring constant K and the mass M. Right? If you want to determine the damping ratio, then that's given by the damping constant F over 2 root M times K. So that's our mass spring damper. So our fourth example for modeling is going to be a hydraulic ram. In this particular model, we're going to start with a very simple model, and then we're going to add a few little bit of, few minor complexities to it. So what we're going to start with in terms of our assumptions, well, you can see the parameters listed here on the left-hand side. Q is a flow rate into the fluid, of hydraulic fluid into our, ram, or into our cylinder. P is the resultant pressure in the ram. M is the mass of the ram, and x is its displacement. A is the area of the RAM, so that's the cross-sectional area, which we're not seeing because we're looking at a cross-section. But if we were to look from the other projection, this thing will be, circular, so it would be the area. So if we say this is the mass of the RAM here, that cross-sectional area. So this is the RAM inside the cylinder looking end on. Okay, so that's the area. So from that we can start to, well, first of all we're going to make some assumptions, some simplifying assumptions. So we're going to neglect the RAM inertia, which means we assume m equals 0 for now, and we're also assuming that the fluid is incompressible, which is a fair assumption for hydraulic fluid because it is pretty incompressible. We're going to assume rigidity in the pipeline and the cylinder, and also that there are no losses around the sides of the piston. That is a loss-free system. Right, so those are some of the basic assumptions that we're making. What we want is the output position of the RAM as a function of our input, which is the flow rate into this cylinder here. So we're looking at the relationship between RAM displacement and the flow rate of hydraulic fluid into the RAM. So what are our governing equations here? Well, the first equation is continuity of flow. If we're saying it's incompressible, then for every meter cubed, or probably millimeter cubed, of fluid which is pumped into this cylinder, that means there has to be a displacement of the RAM by an equivalent volume, because this fluid is incompressible. So if fluid is being pumped into here, it's going to have to shift this RAM to accommodate the additional volume of fluid which is coming in. So the inflow rate of fluid in, let's call it millimeter cubed per second, has to equal the change in area here, or the displacement times the area, in millimeters cubed per second. Right? So you have cross-sectional area times the rate of displacement. Right? So our flow rate Q has to equal the cross-sectional area times the rate of displacement, or the speed of movement of the RAM, which is the rate of increase in volume of that in that cylinder there. So very simple equation, simple differential equation. It's a first order differential. It just has one dot on top of the x there. And so we can take Laplace transforms of this element by element again. This is going to be Qs equals A is a constant, xs times s, assuming 0 initial conditions. In other words, that the RAM is stationary when we start this movement, this process. If the RAM is moving, if it has some velocity, then you're going to have non-zero initial conditions and an additional term here, but we're ignoring that, so we can say there's no additional terms. So that's our Laplace transform, and that's actually gives us the answer. Simple as that, because what we're looking for is the output position over the flow rate. And so because these very simplifying assumptions we made, then it's an extremely straightforward equation whereby the output over input is x, input is q, is 1 upon SA, which you could also write 1 upon A times 1 upon S. I write it like that just to make it easier to see exactly what's going on here. Where do you get a 1 upon S from? That's something we've seen before, right? When we've been dealing with Laplace transforms and so on. If you have an integral term and you take the Laplace transform of an integral term, so that would be Laplace transform of integral of some function f of t dt gives us f upon s, right? Where you have a function f integrated and you're taking the Laplace transform of an integral expression, that's where you get the 1 upon s. So you do get it from the step function, but you also importantly get it from an integrator. Whenever you have an integrator or a 1 upon s term that doesn't come from a unit step but comes from an integrator characteristic of a system or an integrator control element, which we can also add as a control element, it always has a beneficial effect on steady state accuracy, but it has an adverse effect on stability. It makes the system more unstable, and we'll look in more detail about why that is as we go through the course. Right. So what we're going to do now is say, okay, same RAM. We had a very simple system. Just as you add volume, it causes an effective change in volume of the cylinder, and the piston moves as a result. Very simple. But what we're going to add now is just a couple of additional assumptions, or ease some of the limiting assumptions, so that we can get a more representative model. And these are the ones that we're going to ease. We're going to add some mass to the piston. We're going to add a leakage coefficient around the piston. So what we're going to have now is that not all the fluid that gets pumped into the cylinder is going to contribute towards that change in volume of the cylinder or the displacement of the ram accordingly. Some of the fluid that's pumped in is going to escape here. Right, so this is the fluid that pumped in that is going to result in change of volume, and this is going to result in loss of fluid through leakage. Now we've got some additional kind of additional terms in our equation. Most importantly, we have this variable P. P is pressure. So as our pressure increases inside that cylinder, then our leakage increases, or the volume leakage is a function of pressure times this leakage coefficient Ks. So I suppose you could argue that's the size of the gap in the seal or something, right? So the Ks times pressure will give you the rate of change of volume due to leakage, the volume leakage. Now we have a second equation. Before we only had one equation because there's a very simple relationship, but now we've got two equations because we also have mechanical motion due to the mass. So we've also got a force balance taking place here, which is the balance between the force acting on the cylinder, so on the piston rather, due to the pressure in the cylinder, and the balancing element is then the acceleration rate of this mass, so x double dot t times m by Newton's second law. Mass times acceleration, or force equals mass times acceleration. So we have this kind of balancing equation. The force on the left hand side is AP, that's the area times the pressure. F equals area times pressure, and that force equals the mass times the second derivative of x, which is our position, so this is A. So we come back to F equals ma then. Right, now what you notice with these equations is that you have the variable P in both of them. So P basically links these two equations together, and also we can see that we know P is what you describe as or what I describe as an internal variable. In other words, it's a variable, but it's not one that's either part of the input that we're interested in or the output. We know that x of t is our output, and we know that's output, and we know that q of t is our volume flow rate. This is our input. We can see that neither of those are p, so therefore we're not interested in p. We actually want to eliminate that. So we can eliminate p either by combining these differential equations here into one large differential equation and then take Laplace, or we could take Laplace first and then combine them. So let's take Laplace. Let's see which way we want to do it. Yeah, let's take Laplace of each of them and then we can combine them. Right, so I'm actually going to do it over here. Try to typically, just what I'll do is duplicate this. Give me one quick second here. I'm just adjusting my slides to give me a bit of space so I can do our little Laplace transform. All right, so let's take the plus of each of these. So you have q of s equals, I probably should write here, taking Laplace. Yeah. A x of s times s plus k s ps. Right, and then for the second equation, you have a ps equals m s squared x of s. Let's rearrange this one to give ourselves an expression for ps. All right, and then we can combine them. All right, we're going to take this, put it into here. Q of s equals a x of s, as x of s, and ks times m upon a s squared x of s. As plus m upon a ks s squared. So that's our x upon s. It's showing probably a little bit more neatly here. All we've done, we're dividing by a. We can express that in our standard form, which looks just like what we had before for the first order system, because this looks like our time constant form of a first order system, but we have the extra s, and that extra s means that actually it's a second order system, but it's not really called a second order system. This is called a first order type 1 system. In our first order type 1 system, what's tau going to be? Tau is going to be this, right? Ksm upon a squared. And what's k going to be? This one, 1 upon a. So again, our time constant is a function of the elements in our system, and as is our what we call open loop gain. So with this one RAM, hydraulic ram, we've looked at a very simplified system that's given us a pure integrator, but then we added some assumptions which is around loss of fluid in the system and also the mass of the piston, and by adding those elements back in, it turned into a different equation. And effectively what we have is sort of the integrator here times a first order system here, right? So that's what we ended up with, a first order type 1. So this is our pure integrator that we saw when we didn't have those additional elements of mass and loss. And then this one here, these elements, this first order system, this comes from the mass and from the loss elements. K is 1 upon a, tau is Ksm upon a squared. So we've got, what types of system do we have? We've learnt about first order system. We've learnt about a second order system, and well, when I say these, it's the standard form of each one, right? The first order system in the time constant form, or in the ZKP form. Second order system, which is the second order prototype transfer function, which is a function of natural frequency and damping ratio. And then we've got a simple integrator. So we looked at that, and then in this last sort of iteration of the example, we got the first order type 1 system. So we've got 4 different types of system, like in the standard forms we've looked at for each of these. So that's it for mathematical modeling. We've kind of done that part of the course now. So we did Laplace block diagrams, and then how we actually create mathematical models of different simple systems.